Okay, so for today, the announcements are pretty similar to yesterday. So firstly, the big assignment this week is the mission checkpoint. So please send it in on Canvas. And this is considered a commitment to participate in the semifinals. And also I added an additional note to please make sure your team has the correct members before submitting, because if we do a team modification after you submit, then it erases your submission. So that happened to one of the teams already, but it's great to make sure your members are correct before submitting so you don't have to submit twice. We will hear from a few students after class today. The submission is still open if other people want to submit flash talks for next week. And the certificate form, please fill out your personal data if you would like a certificate for this course, and that'll be due September 10th. All right, and then I'm very excited to introduce Dr. Michaël. He's coming to us from the University of Liège in Belgium. He will be talking to us about exoplanets and astrobiology. And he has a very strong background in astronomy and exoplanets. So he studies potentially habitable rocky planets and orbits around nearby very low mass small stars. And he co-discovered hundreds of exoplanets, and he's responsible for the discovery of the famous TRAPPIST-1 system, which we might be hearing about more today. So thank you for joining us, and we're very excited to hear from you. Are you able to unmute yourself? Oh no, oh I think we
Okay, thank you.
There we go. Sorry about that.
No problem. I'm very pleased to be here today and to give this presentation. So I'm going to share my screen if it's fine for you. So do you see my slides?
Yes, looks great.
Okay, so yeah, since I'm a kid, I'm fascinated by stars, and I think most people are. And I keep wondering, are we alone? Is there life beyond our solar system around these stars? And what is really exciting is that this question is now at the forefront of science. It has been pure speculation for centuries, but now it's really something we could get an answer very soon. So first, I would like to give a summary of our cosmic, let's say, neighborhood and our direct neighborhood, our environment, which is a solar system. Our solar system is composed of 8 planets, 4 rocky planets that are relatively close to the sun, and then we have 4 giant planets further out, and there's a huge difference in mass and size between the 2 categories of planets. And our planet in the solar system is very special because it is just our planet, but this is the only one that sustains large amount of liquid water on its surface. And so in astronomy, we call this an habitable planet. And water is a very special molecule in liquid phase. It enables a very complex chemistry, which is really at the basis of life as we know it. And so if you look at all organisms, a living organism on the Earth, they all depend critically on water. We are human beings, we are composed of 70% of water. And still, it's fascinating to consider that liquid water is only a tiny fraction of the composition of our planet. So you see this tiny droplet here on this dry Earth. It corresponds to 0.02% of the mass of the Earth, and still, this is what makes the difference between having a biosphere and no biosphere on our planet. So, what we would like to do to search for life elsewhere in the universe is to find, when we say Earth-like planet, we want to find planets that are rocky and have liquid water on their surface, so habitable planet. Now, we know from a basic physical consideration that you can't have liquid water on the surface of a rocky planet anywhere. You need to be at the right distance or within the right distance range to the star. So if you go too close to the star, of course, water will evaporate. If you go too far, it will freeze. So it is illustrated here with this green annulus, which is called the habitable zone of the sun, or circumstellar habitable zone. And you see, of course, that the Earth is within this range of distance for which liquid water is possible. Venus is a bit too close. Mercury is way too close. And further out, you have Mars that is at the outer edge of the habitable zone. So this is what we want to do. We want to find planets that are orbiting within the habitable zone of their star. Now, Venus is close to the habitable zone. Mars is within or at the limit of the habitable zone. But thanks to astronomy first and then to space exploration, we know that these worlds are not at all habitable. They are very different from the Earth. Venus has an atmosphere which is 100 times denser than the one of the Earth, very rich in CO2, very acidic too, and which translates, thanks to the huge greenhouse effect that is ongoing there, to surface temperature of something like 300, 400 degrees Celsius on the surface, huge pressure, and also very acidic conditions. So not at all an habitable world. And Mars has the opposite problem. It is a tiny planet, and it has lost its atmosphere. There is still a scarce atmosphere, but not enough to make possible water to exist in liquid phase on the surface. So basically, our two neighbor terrestrial planets are dead worlds, for what we know. We can still think about microbes living under the surface of Mars, but clearly Mars is not an habitable planet like I have defined. And to find such a planet, we have looked everywhere in the solar system, there is none. So we have to look to the stars and to search for planets around the stars. And interestingly, the idea that planets exist outside our solar system is pretty old, in fact. It dates back to the origin of the Copernican revolution. So a few decades after Nicholas Copernicus proposed that the sun was the center of the universe, surrounded by the planet orbiting around it, a philosopher called Giordano Bruno, an Italian philosopher, proposed that the stars were just suns also, but very far away and orbited by their own cortege of planets, including inhabited planets. And we are in the 16th century. Yeah? At that time, they're not talking about exoplanets, but this is basically the same. And even the great Isaac Newton, that basically invented modern science, also proposed that the stars could also have planets around them. But it took centuries to confirm that stars were indeed suns. The demonstration came at the end of the 19th century, basically. And it took even longer to confirm that exoplanets did exist. And the first confirmation came in the, let's say, 80s. So at the end of the 20th century, in the 80s, there was a mechanism that was proposed to form planets around stars, around the sun, notably. It was designed to explain our planetary system. And it was proposing that around a young star, you have what is called a protoplanetary disk of basically gas and dust. The dust particles collide with each other, accrete, form bigger and bigger bodies. And at the end, you get planets. And these planets, if they are massive enough, they accrete the gas, and you have giant planets. And this was pure theory until the 80s and 90s, where we had our first direct detection of this protoplanetary disk, notably thanks to the Hubble Space Telescope, that made these images of young stars. And each time Hubble observed a young star, there was a very young star, a few million years old, there was a large amount of material forming a disk around it. So it was the first indication that the environment to form planets existed elsewhere in the universe. And then a few years later, two Swiss astronomers that are shown here, Didier Queloz and Michel Mayor, detected for the first time a planet around another sun-like star. And it was a big surprise, notably because it was the first exoplanet, but also because this planet didn't look at all like planets of our solar system. Because this planet was a giant planet like Jupiter, but on a very short orbit of a few days orbital period around its star, while Jupiter has a period of 11 years. So it is much further away. And this discovery was enabled them to win the Nobel Prize in Physics a few years ago. Okay, and now, so this discovery happened in 1995, and now, nearly 3 decades later, we know more than 5,000 exoplanets. So this discovery really initiated many ambitious projects to detect more and more exoplanets. And so what you have here is a cumulative number of detection as a function of the year. And at the end of the 20th century, there were really a few exoplanets known, but it grew nearly exponentially. And now we have 5,000 exoplanets, more than 5,000 exoplanets known. And each day, every day, there's new exoplanets that are found. And with such a large harvest with such a large a sample of exoplanet, we can already draw a very profound conclusion, which is that when you look at the star in the sky, you can be sure that all the stars that you see have their own planets. It was just, let's say, speculation at the time of Giordano Bruno, but now we are totally sure nearly all stars in the universe have their own cortege of planets around them. But this planetary system, we thought that they would look like our planetary system, and we were totally wrong. In fact, these systems are much more diverse than we thought. We have systems that are extremely compact with many planets very close to the stars. We have systems when we have a giant planet super close to the star, we call it a hot Jupiter. You have planets around double stars, triple stars. You have planets that are orbits that are not circular, like in the solar system, but very elongated, elliptical. We know that there is in our galaxy billions of free-floating planets, so planets that have been formed around the star and ejected into the interstellar void. And there is also even planets around dead stars, what we call white dwarfs, neutron stars, and so on. So basically, there is a real zoo of planets out there. And notably, to explain this presence of planets very close to the star, we had to rebuild our models for the formation of the solar system, because we understood that this model could not apply to planets, to all planets of the universe. There was some ingredients or mechanism lacking, and one of them is called the migration mechanism. So it is illustrated here in this figure. These are snapshots of hydrodynamical simulations where you have a planet. So this is the small white dot here, which is still surrounded by the gas in the protoplanetary disk. This gas, after a few million years, is basically eroded and ejected or accreted by the star. But during a few million years, the planet, when it's forming, is surrounded by this gas. And the simulation shows that the planet is going to interact with the gas to form big structures. You see these spiral arms going up and down here. And these structures are going to interact gravitationally with the planet itself and make it move inward or onward. And sometimes the motion can be quite dramatic. You can have a planet that forms very far away and move extremely close to its star. And what is interesting is that we can really now witness this kind of mechanism. So you see on the right, you see a gap that has been created. So when the planet is massive enough, simulations tell us that you should have a gap. All the material basically fall on the planet or is discarded, is ejected outside or inside. And now we have the capability to observe with a very high resolution young protoplanetary disk. And we see these gaps. We can see really the traces of the formation of planets thanks to our data. So what you have here is a protoplanetary disk around a very young star. It was observed by the ALMA radio telescope in Chile. And you see all these gaps here. We think they are related to the presence of planets that are there, still interacting with the gas. Maybe they're migrating inwards, outwards, but it's clearly the fingerprint of the formation of planets. Now, we're talking about astrobiology here, so we can now focus on planets that are said to be potentially habitable. So we don't have thousands of them detected so far. It's only a few dozens of them, but they are very interesting. But we can't say if they're really inhabited or not. We would like to make the next step, which is to study these planets in detail and maybe search for traces of life on this planet and answer the question, is there life elsewhere in the universe? And so it's not easy, as you can imagine. So the obvious way to do it would be to use a very big telescope with a very high resolution. So the bigger the telescope, in theory, the higher the resolution. So the more possible it is to separate the light from the star and from the planets. And so if your telescope is powerful enough, you should be able to make images in which you see the planet around the star. You would take the light coming from the planet, study it, and search for traces of life. And what you have here are real images of exoplanets that were imaged by big telescopes. So on the right, you have 3 planets around a nearby star. And you see the star looks weird. I'm going to explain why afterwards. The light of the star has been suppressed. And here it's a very recent result. It's basically a planet that is still embedded in its disk, into the protoplanetary disk. So it's still interacting with the gas, as I explained, and it's creating some structures in the disk. So the planet here is shown as a C, and the spiral structure are created by the planet. Now, if we can make this kind of image where we see the planet, and if we are talking about an habitable planet, or a potentially habitable planet, what we can do is spectroscopy. So we're going to take the light from the planet, we're going to spread it in different wavelengths, and we're going to look at the distribution of the flux of the light at different wavelengths. So we are going to obtain what is called spectrum. And a spectrum of an object is rich in information about the composition of its outer layers, because the outer layers are going at some specific wavelength to absorb the light coming from the deeper layers. And for a planet, when I say outer layers, I'm talking about what is called the atmosphere. So by studying the spectrum of an exoplanet, we could study its atmospheric composition. And it is illustrated on the right here. You have the spectrum of Venus in the infrared wavelength range, of the Earth and Mars. All 3 planets have CO2 in the atmosphere, so we have a clear signature of CO2 for the 3 planets at a wavelength that is basically given by particle physics, by quantum mechanics. But for the Earth, you can see that there is other structures that are due to other molecules in the atmosphere, notably water, ozone. And these are very interesting molecules that we could relate to an activity, biological activity on the surface of the planet. And this is illustrated here. So what you have here is a tree. What I want to illustrate here is that life alters the composition of the atmosphere of the planet. Life is really something that is part of basically the global planetary system of the system of the planet itself, and it impacts the atmospheric composition of the planet. So this tree, for instance, sucks water by its roots. It absorbs carbon dioxide by its leaf, and it's using the energy from the sunlight to break water and to build up from carbon dioxide, to build up molecule rich in carbon, organic molecules, notably sugars that are going to give to the tree the energy to grow and to prosper and to reproduce itself and so on. And in the process, because you are breaking water, you are releasing oxygen. So it is what is called oxygenic photosynthesis. And so through this mechanism, during the billions of years of life of the last billions of years on Earth, since the, let's say, advent of photosynthesis on Earth, we had some accumulation of oxygen in the atmosphere. So it is illustrated here on this diagram. You see the evolution of the content of oxygen in the atmosphere. It was very low since the beginning of the history of the Earth. And then at some point, thanks to photosynthesis, it increased in the atmosphere to reach an equilibrium value of about 20% of abundance in the atmosphere. So this is just an example. This is one metabolism. There are plenty of different metabolisms, but they could all alter the composition of the atmosphere of a planet. Now, I mentioned that the most obvious way to detect an exoplanet would be to use a big telescope, but it's not enough to have a big telescope, because if you have a big telescope, basically you can have the resolution to see 2 things that are separated from each other. You can detect very faint source, like this firefly here on the lighthouse. But when your very faint source is just very close to a very bright source, just like our planet that will be very close angularly to its star, you have a problem not only of resolution, but also of contrast. So here, if I turn on the lighthouse, you don't see anymore the firefly. And it's because there is the glare of the lighthouse is too strong, and it's completely suppressing, hiding the signal coming from the firefly. And it is exactly the same situation we have with exoplanets. So if we want to image exoplanets, we have to find a way to suppress the light from the star. So we have ways to do it, which are notably inspired by nature. So we have a big satellite around the Earth, the moon, and from time to time, the moon passes in front of the sun. It has exactly the same angular side, just by chance. And when it does so, you see the outer layers of the sun atmosphere, what is called the chromospheres that appear. But when you don't have the moon in front of the sun, you don't see the chromosphere because it's totally lost in the glare of the disk of the sun, which is much brighter than this chromosphere. So we can use similar tricks to try to hide the light coming from the star. This is called coronagraphy. We have also techniques that are called interferometry, nulling interferometry, that are all based on the suppression of the light of the star to see its surrounding, to be able to detect faint source around it. But when we apply these techniques as they are to stars now, we don't have the capacity to detect terrestrial planets. What we are able to detect is very big, giant planets, very far away from the stars, and that are still very young and so very hot, for which the contrast with the star is not too small. So if we want to apply this to the detection of terrestrial planets, we need a very big, powerful telescope, and notably there is a project of space telescope that should be able to do it, which is illustrated in this video here. So this telescope would be composed of two parts. You would have the optical part of the telescope itself, and you would have a kind of artificial moon that would go very far from the telescope to hide the star, and so to be able to see the faint planets around the star by suppressing physically the light to reach the telescope, the light coming from the star. Well, this is called a star shade, and this is the technology that hasn't been still demonstrated. So if this project exists, at some point, they will probably exist, but it will take decades to have them operational, to be able to make images of Earth-like planets around sun-like stars. Nevertheless, and fortunately, this is not the only way we can detect and study exoplanets. And in fact, most of the planets that have been detected indirectly. And notably, thanks to a method that is illustrated here by this shadow of an invisible man. So even if you have an invisibility cloak, you won't be totally undetectable, because if you are walking in the nature, you will have your shadows that will appear, and you could be detected. And we can use this principle also to detect exoplanets that we can't see, but just to detect basically the shadow due to the interaction with the light of the star. Here it's the interaction with the light of our sun, this shadow. But in the case of exoplanets, we are going to use what is called the transit. So in astronomy, a transit is the passing of a small body in front of a bigger body. And so we can define a planetary transit, which is the passing of a planet of our solar system in front of the sun as seen from Earth, which is something that can only happen for the two inner planets to the Earth, which is Mercury and Venus. All the planets in our solar system lie within the same plane, which is called the ecliptic plane. And so from time to time, we have Venus of the Earth that pass in front of the sun. So this is a transit of Venus in front of the sun. And you can see how Venus, this small black dot, is small compared to the sun. It's really a tiny thing compared to the sun. For exoplanets, we are not able to make such high-resolution image where we would see the planet in front of the star. But what we can do is to monitor the brightness of the star. And when the planet passes in front of it, because it hides a part of the disk of the star is going to look a bit dimmer, a bit less bright. And so this is illustrated in this, what is called a light curve. So this is the evolution of the flux of the star measured with our telescope as a function of time. And when the planet passes in front of it, we have a transit signature, which is a dimming, decrease of the flux that we measure. And this decrease of flux is directly proportional to the area of the planet relative to the area of the disk of the star. So by measuring the depth of this dimming, we have directly an indication of the size of the planet. The bigger the planet, the larger will be the dimming. And as we know quite well, we can estimate quite well the size of the stars, we can directly infer the size of the planet. And also, by looking at the periodicity of the signal, we can measure the orbital period of the planet, and we can infer from that, and using Newton gravitation laws, we can infer the distance between the planet and the star. And we can notably say if the planet is within the habitable zone of the star or not. With the other methods, we can also measure the mass of the planet. So you have the mass, you have the radius, so you have the densities. So you can put constraint on the composition of the planet. You can notably infer if it's a rocky planet, which is very dense, or if it's a big, puffy, bloated giant planet for which the density is much lower. And last but not least, we can also study the atmosphere of the planets where we don't have any image of the planet itself. So it is based, again, on the transit. So when the planet passes in front of the star, you have the thin atmospheric annulus around the planet that is not totally opaque to the light coming from the star going in our direction, that is going to absorb or scatter light going from the star in our direction. And so only a fraction of this light is going to reach our detector. And it will be wavelength dependent, meaning that if you have, for instance, in the atmosphere, you have a molecule like CO2 that absorbs specifically at a given wavelength or at different wavelength, at these wavelengths, you will have more absorption by the atmosphere, so you will have less light reaching our detector. So what we are going to do is to measure the size of the planet, measuring the transit depth at different wavelengths, and we will be able to obtain a spectrum, an absorption spectrum, that will tell us, that could reveal the presence of an atmosphere and also tell us about the composition of the atmosphere, just by looking at the amount of light that we receive on Earth from the system during transit and outside transit. And also there's another method to study the planet atmosphere. We can observe at the opposite phase when the planet is behind the star. So at some point, the planet will disappear behind the star. We call this an occultation. And if you observe, notably in the infrared, you will be able, if you have a very precise telescope, you will be able to see a small dimming, which is caused by the disappearance of the small contribution of the planet to the global flux of the system. So a planet is a very faint object compared to its star, but if you're precise enough, you will be able to detect the disappearance of the emission of the planet itself when it is hidden by the star. It's just, again, by monitoring the flux of the system as a function of time. And if you do this at different wavelengths, you will be able to reconstruct the emission spectrum of the planet. Now, this is the theory, and it has been applied successfully to many giant planets. But if you want to apply it to potentially habitable Earth-like planet, you have a problem, and it is a size problem. So you have, again, here, Venus in front of the sun. It's a real image. You have to think that you want to detect not just the pacing, the transit of Venus, so to reveal the presence of the planet, but you want to detect the signature of the light passing in its atmosphere. So you want to detect this tiny fraction of light emitted by the star that is going to pass through the atmosphere. And in terms of numbers, we are talking about numbers. If you take the Earth in front of the sun, we are talking about, let's say, some signals of the amplitude of 1 part per million. So much, much less than 1%, very, very tiny signals. And unfortunately, we wouldn't be able to do it with current technology. And even if we could do it in theory, the star itself is not stable enough to make possible detecting this kind of tiny, tiny signal. But there is a shortcut, and a very easy one, which is to try to detect Earth-sized planets, but in front of tiny stars. If the star is smaller, and significantly smaller, then the relative amplitude of the signal of the planet itself passing in front of the star, but also of its atmosphere passing in front of the star, will be larger. It's scaled with the square of the radius of the star, inversely with the square of the radius of the star. And so when you do the math, you can conclude that it is possible with current technology to study an Earth-like planet if it transits around a tiny star, which would be 10 times smaller than the Sun. We call this an ultra-cool red dwarfs. And these red dwarfs are everywhere in the galaxy. In fact, most stars in the galaxy, in the universe, are red dwarfs, are smaller, colder than the Sun. But also, interestingly, you can't see none of them when you look at the sky. Because they are so cold and small, they emit most of the light in the infrared, you are not able, with the naked eye, to see any of these stars, even if they dominate totally the population of the galaxy, of the universe. It is illustrated here. You have an image of Alpha Centauri, which is the nearest star to the solar system. It's visible only from the southern hemisphere. And you see in this image that was taken with a very good telescope, you see a tiny dot of light in the bottom. This is Proxima Centauri, which is a star that is basically orbiting around Alpha Centauri. Alpha Centauri is a binary star, but there is another tiny red dwarf that is orbiting around Alpha Centauri, very far from the binary. And in fact, it's closer to the Earth than Alpha Centauri itself, but you can't see it. It's way too dim to see it. You need a telescope to see it, even if the nearest red dwarfs. So what is interesting with these red dwarfs, they are everywhere, they are ubiquitous. Now with our current telescope, we can detect plenty of them. And furthermore, if you look at the habitable zone of these stars, it's very close to the star itself. Just because these stars are so cold and small, they emit much less light per second than the Sun. So to have temperatures that are good enough to have liquid water on the surface, you need to have the planet much closer to the star. So the habitable zone of this star is much closer than the one of the Earth. And also, if you look at the ultra-cool red dwarfs, so the ones that are the smallest, that are basically the size of Jupiter, we are talking about orbital period of a few days for the planet in the habitable zone. And it makes the detection of transit much easier because we have much more transit. If you take an Earth-like planet, you have to wait a year to have the planet pass in front of the star. So you need to be lucky to detect a transit, and you have really to observe at the right time. For these planets, if they exist, it's much more frequent, the transit. So it's much more easier to detect the transits. So this is the principle. We could study Earth-like planets if they transit sunlight, these tiny ultra-cool red dwarfs, but we still need two ingredients. We need a telescope able to study this planet and to study the atmosphere of this planet, and we need to detect these planets. So let's take first the first ingredient, which is the telescope. And for now, there is only one telescope that could do this job to study the atmosphere of a potentially habitable planet around this red dwarf, an ultra-cool red dwarf. It is the James Webb Space Telescope. It was launched at the end of 2021. It is the most sophisticated and ambitious space telescope ever launched by humanity. It's this telescope, in fact, it's a 6.2 meter telescope in diameter, the biggest space telescope ever. This telescope is so big that it had to be folded to be put into a rocket to be launched into space, which puts a lot of challenges, technological challenges on the mission, because you had to imagine a telescope which is like an origami that has to deploy in space and to be able to take the right shape in space to operate once it has been launched. And so, fortunately, NASA managed to succeed building this telescope. It was launched by ESA, and it is now fully operational. So we have the right telescope. Now we need to detect the planets. And there is two projects that can do the job, that are designed to do this job, detecting small planets, transiting small stars, so small red dwarfs. There is a mission that is led by NASA, which is called TESS. It is a satellite which has 4 tiny telescopes of 10 centimeter diameter, so really, really small telescopes, that is basically monitoring all nearby stars, searching for transits of exoplanets. And there is a project I'm a very fan of, because I'm leading this project, which is called SPECULOOS. It is a network of ground-based telescope. So the advantage when you operate from the ground is that you can build for much less money, bigger telescope. So it's a network of 1 meter robotic telescope spread between Chile, Tenerife, and Mexico, and which is targeting especially, very specifically, the smallest nearest stars. So these ultra cool red dwarf that I mentioned. So SPECULOOS has only 1,600 targets. TESS has more than 200,000 targets, but still, I think that the best targets for the search for biosignature will be found by SPECULOOS, because all the planets that are found by TESS, could be found by TESS because the telescopes are so small, will be found around bigger stars for which we won't be able to study the atmosphere, except if the planet is bigger, and we are very lucky. And so SPECULOOS started in 2011 as a prototype. So before having the project fully operational, I initiated a prototype on a small robotic telescope that my colleague Michaël Gillon and I installed in Chile in 2010. So we call it TRAPPIST in reference to, because we are Belgian, it's a reference to TRAPPIST beers for those of you who knows, who have heard about them. And so this telescope, it's a 60 centimeter telescope, it's relatively small. And from 2011, we use it to observe, to monitor regularly 50 nearby ultra-cool red dwarf. And at that point, there was absolutely no planet that has ever been detected around this kind of tiny stars. And in fact, there were even papers saying these stars are too small to form planet of the size of the Earth. Nevertheless, we wanted to try. So we observed these 50 targets, and among them, we detected this signal here, which is shown on the right. So you see here the evolution of the flux of the star as a function of the time during a night in 2015. And you see some jitter, and you see a drop of brightness in the middle of this what is called light curve, which correspond exactly to what we would expect from the transit of an Earth-like planet in front of the star. And here on the left, you have the position on the sky of the star. It is in the Aquarius constellation, doesn't matter much. And so we observe once we had a transit, we observed very intensively the star, and we could confirm there was a planet around the star. Then we had an indication of a second planet. We could confirm the second planet. And in 2015, observing this second planet, we had something really, really exceptional in our data. So we use a big telescope, an 8-meter telescope in Chile. And by observing the transit, we could see that it had a very weird shape. And in fact, you have here a decrease of the flux, and a second decrease, and an increase, a second increase, a third increase of the flux. And the only way to explain this evolution of the flux that is measured is by advocating that, in fact, it's not one planet, but 3 planets that pass at the same time in front of the star. And this wide hypothesis turned out to be true, because when we observe more and more the system, we could confirm the existence of more planets, a third one, a fourth one, a fifth one. In 2016, we had to observe with the space telescope of NASA called Spitzer. We observed 500 hours continuously the system to crack the system, because clearly it was a very complex system. In our 500 hours of observation, we had 34 transits of exoplanets that we could relate to transit we had observed from the ground and crack the system and show it was composed of 7 Earth-sized planets in very short orbit around the star. And so it is illustrated here. So this system, all the planets have basically the same size, the one of the Earth, and they are forming a super compact system. The inner planet has a distance to its star of 1% the Earth-Sun distance. The outer planet has a distance to the star of 6% the Earth-Sun's distance. In fact, the planets are so close together that they are within a few Moon-Earth distance from each other. So if you were on the surface of one of these planets, you would see the other planets like you see the Moon. You would see the structures, you would see, I don't know what is there, but the cloud, the continents, whatever, you would see everything like you can see structure on the surface of the Moon. And interestingly, if we look at the habitable zone of the system, we see that 3 planets are falling within the habitable zone of this star. Sorry, One of them is at the inner edge, one of them is at the outer edge, and two of them are too close to the star to be habitable. And because the star is very nearby and very, very small, we can study this planet with James Webb, and notably to search for atmosphere, to search for even traces of life, if life is there on this planet. So before doing so, we observe the system intensively, and we could measure very precisely through a method I don't have the time to describe, the radii, but also the masses of the planets. So we had extremely precise densities. In fact, this is the most, the best characterized planetary system outside our solar system. In terms of precision, we have on the size, on the mass of the planets. And when you look at the density of the planet, it's given as a function of the illumination they receive from the star. You can see that if you compare to the Earth and Venus, all the planets seems to have the same density, meaning they probably have the same composition. The 7 have the same composition, but the density is a bit lower than the one of the Venus and the Earth, which suggests that this planet could be more rich in volatile elements, notably in water or methane or ammonium, or alternatively, they could also have a smaller core than the one of the Earth and Venus. But clearly, these are terrestrial planets. So here it's an illustration, it's an artistic view to show you what you could see if you were on the surface of this planet. You would see, as I said, the other planets like very clearly in the sky, and also the star itself, because it's a very small star. It's 10 times smaller than the sun, but because the planets are so close to the sun in the sky would be something like 10 times bigger than our sun in the sky. So it would be a huge ball in the sky and emitting nearly only red light. And if you had eyes sensitive to infrared, you would see that it emits a lot of infrared lights. No blue light, because these tiny stars are too cold to emit a lot of blue light. And we could say that these planets are Earth-like planets, but not in whole aspect. Clearly, there are alien planets, weird planets compared to the Earth, notably because they are so close to the stars, they should always show the same hemisphere to the star, just like the moon to the Earth. This is due to the tidal influence of the star itself, which is so close. They should have been trapped. This one is called synchronous rotation. And so you have a phase, an hemisphere that is constantly day-side. So meaning you don't have any day-night cycle here. If you are on the day side, it's constantly day. If you are on the other side of the planet, it's eternal night, and you don't have any cycle. And in terms of climate, can lead to very wet climate. You could have a very hot day side, a very cold night side, and in between, you could have a more temperate ring, what is called a terminator. If the atmosphere is dense enough, you have good redistribution of heat from the day side to the night side. If it's scarce, you could have such a configuration. And also something that is interesting and also very different from the Earth itself is that the star is very different. It's small, it's cold, but it's not quite at all. These tiny stars have a very complex magnetic field. They have fully convective structures, and so they have a very dynamical magnetic field. They have a very long lifetime also. The lifetime of TRAPPIST-1, the star, is about 1 trillion years, whereas the universe is only 13 billion years. So it's a baby star. And as all baby entities, it's very active. And notably, it emits a lot of X-ray, UVs, and also charged particles. The same amount per second as the sun, but because the planets are so close to the star, it could be a problem for the survival of an atmosphere around them. Because by receiving so large amounts of X-ray, UVs, and charged particles per second, you could have an erosion of the atmosphere. So there is a possibility that the planets are, like on this image on the left, planets that have still an atmosphere and maybe habitable condition for the ones that are in the habitable zone, if they manage to sustain an atmosphere despite the adverse conditions. But it could also very well be that they are all airless balls of rocks. And this is the primary question that we want to answer with James Webb. Do they have an atmosphere or not? And we have first observation, first result that have been published very recently. So for the inner planet, TRAPPIST-1b, James Webb has measured the day-side temperature at a given wavelength at 15 microns. And so it is illustrated here in this, on this x-axis, you have the temperature in Fahrenheit and Kelvin, and you have the mean temperature on the Earth. You have the one on Mercury, which is completely baked by the sun. And you have the one that has been measured for TRAPPIST-1b, which for between the Earth and Mercury. And it's a bit too hot to match a model for which would have a Venus-like atmosphere, so a CO2-rich atmosphere that would efficiently distribute heat from the day side to the night side. So it agrees with a model which have no atmosphere, or with models which have, let's say, alternative atmosphere. So atmospheres that do not look like the Earth atmosphere or Venus atmosphere, that could be totally different. So we need more data to be sure, but this is the first result for TRAPPIST-1b. For TRAPPIST-1c also, there's been a similar measurement that has been done, again at the same wavelength. It is illustrated here. It is illustrated differently. So you have here the wavelength. It is model emission models that are shown here for different assumptions, for different hypotheses. And the measurement is this red dot here with the arrow bars that are shown. And it matches well a model for which you would have an atmosphere with some carbon dioxide, but a very thin atmosphere. Not like Venus with a very dense atmosphere, but a much thinner atmosphere, even thinner than the one of the Earth. It doesn't mean there is an atmosphere, doesn't mean there's none. We need more observation, but I would say from this measurement, we can already conclude that James Webb has the potential, the capacity, the instrumental capacity to detect atmosphere on these planets. We just need to be patient to gather more observation. This is what we are doing. Gathering more observation, and at the end we will know if they have an atmosphere, and if some of them have an atmosphere, we will be able to probe the atmospheric composition and maybe find molecules that we could relate to chemical activity, biochemical activity. In the meantime, if you're too impatient for scientific results, you can dig into fiction, because it's personally, I've always been inspired by science fiction, and it's one of the reasons I've probably decided to become an astronomer. And it's really fun to see TRAPPIST-1 incorporated in science fiction works. You can find TRAPPIST-1 in comic books, in novels, even in songs, or even in video games. So this is very inspiring for us scientists to see planets that we detect end up in the fiction and kind of feed the imagination of the public. So TRAPPIST-1 is our first discovery. SPECULOOS now is fully ongoing. So you have here an image showing the SPECULOOS telescope in Chile. They are located in what is called the Atacama Desert, which is the driest place on Earth. It is a high altitude desert with nearly no clouds, perfect condition for astronomy, nearly no water. So very harsh condition for life, but very good condition for astronomy. And so it's normal that we put our telescopes there. If at some point in your life you have the opportunity to go to the Atacama Desert, I can assure you, if you go there and observe the sky, when there is no moon, you will have the feeling to be in space, because you will see so many stars, and with such clear sky, that it's something really to live if you have the opportunity. We have also a telescope in Tenerife, which is operational. We have 2 more telescopes coming, and one in Mexico is also operational. And thanks to this network of telescopes, we have detected last year another system, which is called SPECULOOS-2, and we have found a planet which is called SPECULOOS-2c, which is an Earth-sized planet, well, a bit bigger than the Earth, what is called super-Earth, in the habitable zone of a star. Again, a very tiny star like TRAPPIST-1, and it's also a good target for James Webb. So we are trying to get time on James Webb to study also this planet and try to find an atmosphere and to see what's going on if there is an atmosphere on this planet. And we have more planets coming. I can't tell you about it, but we have more results coming. So our survey is now performing, and we have many planets that will be good targets for James Webb in the pipeline that will come at some point. Now, I told you about SPECULOOS, about James Webb, but of course, we won't stop at James Webb. James Webb will be there for maybe 10 to 20 years, but there is even more ambitious projects that are coming to detect exoplanets and study these potentially habitable exoplanets to search for traces of life. So notably, we are building what is called extremely large telescopes on the ground, on Earth. So here, this is an illustration of the European Extremely Large Telescope. It will be the biggest telescope ever. Its diameter of its primary mirror will be 40 meters. So it's half a soccer playground. So it's really, really huge. It is in construction. It should be operational in 2030. And it should be able to study transiting planets, but also to make direct imaging of Earth-like planet around nearby sun-like stars. And I mentioned Alpha Centauri, the nearest sun-like star previously. The ELT should be able to detect an Earth twin around Alpha Centauri and to study its atmospheric composition. So within a decade, we should have the technological capacity to detect an Earth twin around a sun-like star, not anymore around a tiny red dwarf, but really around a sun-like star, and to search for traces of life in its atmosphere. And 1 decade later, we should have space-based telescope, at least one space-based facility that should be able to detect hundreds of Earth-like planets and just study them to search for traces of life. So in this context, I think it's fair to conclude that the question of life beyond our solar system is a very old question, and we are really at the edge of getting an answer. We have the capacity to get first pieces of answer, and within a few decades, we will have the full capacity to answer this question and to conclude if life exists elsewhere in the universe or not. And I thank you for your attention.
Thank you. That was an amazing talk. I learned so much. So I think we have some questions, and you said you have time to stay on for a few questions?
Sure, pleasure.
Great. So Siva is wondering if interference of lights from other stars affects the discovery of exoplanets while we observe from Earth.
So light from other stars could be a problem if our telescope has a very poor resolution, if you are not able to resolve the stars. So from the ground with our 1 meter telescope, which we with SPECULOOS, notably, we observe 1 star at a time with a very good resolution. So we can really resolve the stars. But if you look at TESS, notably, TESS aims to observe many, many stars at once. And so it has a very wide field of view, but with a very poor resolution. It is a price to pay if you want to observe many stars at once. You will have a poor resolution, and so the stars are blended all together, and you have plenty of pollution from the different stars. So it makes detecting planets more challenging. It's doable, but it makes the interpretation more challenging. You have to do observation, follow-up observation to determine if the planet is real or not afterwards.
Thank you. So Agatha is wondering, are there any ways to detect the magnetic fields of exoplanets?
Currently, no, even on giant exoplanets. So for terrestrial planets, certainly not. It's not doable within decades. For giant planets, it could be doable, notably by using polarization methods, observing in polarized in polarimetry, but there's been no detection so far.
Got it. So Ramita is asking, what are the parameters from the data that you collect which parameters help you to decide the geographical features of the exoplanets? And then also, who converts the scientific data into visuals so that the public can understand what the exoplanet looks like?
So basically what we can measure is the size of the planet, the mass of the planet, its orbital distance, its orbital parameters, and that's it. With James Webb, we have first measurement of the temperature, of the flux. It's not even the temperature, it's flux at a given wavelength. So we are kind of doing, well, very simple spectroscopy, but very crude spectroscopy. And that's it. The rest we have basically to use our models to try to imagine what could be out there. So when we make this artistic view, we are interacting with the artistic teams, and we try to reproduce what is possible scientifically from what we know and from the few parameters that we have measured.
Cool.
But of course, there is a huge part of imagination because, yeah, there are so many unknowns in the process.
Great. So Agatha is wondering 2 questions about SPECULOOS. So one is, how do you remove the interference from the Earth's atmosphere to analyze the results? And then since the telescopes are all around the Earth and in different environments, are there any issues or difficulties with correlating their results?
Yeah, so the atmosphere of the Earth is a problem because it's something very variable. So when we are monitoring the stars, try to measure their flux and how they evolve, if you look at the raw measurements, they are very imprecise. The precision is very poor because the atmosphere of the Earth is always varying. You have turbulence, you have clouds, you have plenty of extension coming and disappearing and so on. So what we do is we use the other stars in the fields to correct for this. What we were doing is differential measurements. So we build, I mentioned, we build Lie curves, so the evolution of the flux as a function of time of our target. We do the same for comparison stars in the same field, observed with the same telescope, for which the light has passed through the same Earth atmosphere, and we divide one by the other. And doing so, we remove nearly all the noise coming from the Earth atmosphere. And we can really get then the measurement of the evolution of the flux of the star not polluted by the Earth atmosphere. If you do spectroscopy, you can also use the fact that we know that at specific wavelengths, the Earth atmosphere absorbs, at other wavelengths it does not. So you can clean what is called the telluric lines. So the line from coming from the Earth atmosphere to get a spectrum that is clean from the interference of the Earth. But of course, the obvious solution, if you want to be super precise and study in great detail a very challenging target like an Earth-sized exoplanet, the best is to go to space and to send a space-based telescope. So this is why we rely on James Webb, notably, because it's a space telescope that is not polluted by the Earth atmosphere, and it can observe in the infrared, notably. This is where most of the information about the molecules and atoms in the atmosphere of this planet lie. And unfortunately, the Earth atmosphere is absorbing very efficiently the infrared. So there's nearly no infrared light coming from space to the Earth. So this is why we really need a space telescope to get this information.
Great answer. So Manara is asking, since you are interested in stars, could a mission be developed to explore the possibility of finding other celestial objects around them?
So could you repeat? Sorry, I didn't get it.
Oh, so since you are interested in stars, could a mission or a telescope be developed to explore the possibility of finding other celestial objects besides planets around them?
There's been some indirect detection of asteroids and comets on other stars, because when they are very close to the well, especially comets, when they are very close to the stars, they're gazing a lot, outgazing a lot, and so they can have a huge coma that is going to block the light from the star. So there's been some detection of exocomets. Exomoon, so far there's been no detection. There is many colleagues that are trying to detect these exomoons. They must exist, but like in the solar system, they should be quite small and so very hard to be detected. So far, there's been no detection, but it's just a question of time. I think we will detect them. And yeah, that's it. So if you consider smaller bodies, that's really difficult to detect because, well, we don't have the technology to detect them.
So Cheryl is asking, what are the biggest highlights of your career so far?
The biggest result?
Highlights, like what were you most excited about over your career?
Certainly TRAPPIST-1, the discovery of TRAPPIST-1. It's an easy question. I've been dreaming of detecting such planets and planning the possibility to detect such planet for more than a decade. And to see this planet popping up in the data has been really, really an exciting time. And now we have the capacity to study them. So I would say every time we have more data from James Webb, it's a new highlight for me because it's really super exciting to be able to learn about these planets after having discovered them.
Yeah, definitely. Very exciting for the whole community. So Walter is asking, do you think that planets that are tidally locked to their sun have optimal conditions to harbor life? Or do you think that a day-night cycle is better?
Well, basically, we don't know. In fact, the day-night cycle is something that life had to adapt to on Earth. Theoretically, there's no problem to have life on a planet for which there is no day-night cycle. For photosynthesis, you would have a productivity which would be larger because you don't stop photosynthesis like on Earth during night. It can go on forever. So it could be an advantage. Of course, if you're on the night side, then you have no photosynthesis, so it could be more problematic, but you could still have organisms that are feeding on the limb of the planet, so you can imagine plenty of solutions, but I don't think that is a huge showstopper here, the fact that they are tidal locked for life to exist. The huge problem that I foresee is the absence of atmosphere. So this is really the thing that we want to test. Do they have an atmosphere or not? If there is no atmosphere, then clearly they are not habitable.
So it looks like that's about it for our questions. So we want to thank you again for sharing this time with us. We all learned a lot, and I think it was a really valuable lecture. So thank you so much.